Hello, everyone, and welcome to our presentation on troubleshooting fault EE and EB. So we'll be reviewing these two faults on our Vito dens and Vito Crossel boilers. We're going to have a look at those here in a moment. My name's Scott Boutler. I'm the Academy instructor here in Langley, British Columbia, the Viessmann Western Canadian office. And joining me today from Waterloo, Ontario is my coworker, Academy instructor, Mark Norris. How are things out there in Waterloo today, Mark?
It's good. It's like nice and summery out here today.
Excellent. We got about the same kind of weather here.
Yeah, I heard you're getting a heat wave.
Yeah, not too bad. So actually, I'm in a nice air conditioned. A little chilly actually, in the office here this morning. So I got to turn the heat up a bit.
Get the boilers running.
Get those boilers going. That's right. So we're going to talk today about the EB and EE fault. These presentations are going to be recorded, and we're going to archive these as well. And the idea here is that you'll be able to access the information that we're providing you today, Mark and myself. These are to complement and be a supplement basically to the manuals that would accompany the boilers that are there in the field. We're going to give you some information on how to access those manuals if they're not on site. That's kind of half the battle a lot of times when you're doing troubleshooting, is know where this information is going to be contained. So you can use this moving forward. The idea is also that we're really reaching out to qualified trade technicians. So you know who you are out there, and more importantly, you know who you aren't as far as this information. So it's really meant because we're getting involved in the gas side of your heating equipment, that you have the proper qualifications to kind of tackle these particular faults. Mark's going to be at the controls today. He's going to be, I think, answering some of the questions as you guys have them there. So please get those questions in. We will have a period of time at the end that we're going to, if there's any leftover questions there. Not sure if Mark wants to add anything to that or not, but we're going to.
Yeah, I think what we'll do is you guys all have a question box on your toolbar, whatever you're going to call that. Ask a question. If you want the question answered specifically to you, make sure that that's in your answer, that in your question that you want it answered privately. I will answer you directly. Other than that, any question gets answered to the group so everybody gets it. At the end, there will be a PDF of the presentation, and all of these questions with the answers will be emailed out to you as to whoever's attended this. So you'll have that information for later as well. I'm going to try to keep up with the questions in real time so Scott can get busy in doing his presentation. But again, if there's anything I can't get to or I think Scott should have some input on, we'll hold those to the end, and we'll do those together. So back to you, Scott.
Thanks, Mark. And like I say, there's a lot of, I think, really interesting and good troubleshooting tips that we're going to kind of cover here. And it's going to be a little bit over an hour. We've done this presentation live previously, and it was actually about 90 minutes. So we're going to see if I can get that a little bit shorter here today. But again, it's going to be available to you in the future when you need this information. And like I say, along with the manuals, a lot of the information we're going to cover here today is actually in the manuals. I've just pulled it out and pasted it onto some of the slides that you'll see here. But like I say, before we get started on the actual troubleshooting, we need to have a little quick review of some of the units that you might see this particular fault on. So we're going to get started here on this presentation so it doesn't get too long in the tooth here. So the first thing to look at here would be the boilers. And I'm going to try today for the first time using one of these little laser pointers. Not sure how annoying that's going to be. I'll try to keep it hidden when I'm not, so it's not too distracting. But it would be important here just to kind of detail a couple of areas that I'm talking about as we move through. So you see 4 boilers up here on the screen. And really, when you kind of get into the EB and the EE fault, it's potential that there's about 22 boilers that are influenced here. Now, that seems like a lot. But in reality, the faults are really related to the control. So it's a control-based type of fault information. So we've got some algorithms, some information here in these controls that are looking for specific things to happen. And when those things don't occur, that's when the fault's going to show up. But regardless of a EE or EB, it's any other fault as well as there's a certain amount of expectation that that a control is going to be looking for. And if the event falls outside of that expectation, that's usually when you're going to end up with some sort of an issue, and you need the control to communicate that information to you so you know how to start to navigate and troubleshoot that particular fault. So you see it comes down to the two controls you see at the bottom here where this fault is going to kind of land. And we're going to look at those different faults here, specifically where they occur in the process of the boiler operation here in a moment. But let's have a peek at these different boilers here and identify where you might see them, because this fault or these faults aren't really specific to residential or commercial applications, because some of these boilers you can see in residential and some you might see in commercial applications as well. So it spans both of our worlds as far as gas fitters go. The first one we'll look at is on the far left. So this is the Viessmann B2HA boiler B2TB. It is a boiler that the expectation is you're going to be doing domestic hot water production as part of the boiler itself. It comes already configured for domestic hot water. There is a storage tank that's already built in, the pumps for domestic hot water and the space heating, at least the primary loop application, those circulars are already installed. Sensors are put in for the domestic hot water input for performance. There's also a little external heat exchanger. So the 222F is actually a combi boiler, but it gives you some distinct advantages over just a straight combi because of the storage tank that's in there. So it's a 26.5 gallon storage tank that stores that domestic hot water for use. And then of course, once that tank goes dry, there is the combi portion of it. So the built-in external heat exchanger, which will still heat that domestic hot water up continuously. So you never really run out of hot water with a 222F, like you would say with a boiler heating an indirect tank, where that tank goes cold and now we have to wait for that tank to regenerate that heat before we can actually utilize it again. This one here is continuous. So if we drain the 26.5 gallons of water, you're still going to get that combi effect because the heat exchanger is still going to heat that potable water up before it goes out to your fixtures. Some advantages, obviously, when you talk about loads. So with domestic hot water and combi units, oftentimes when somebody jumps into a shower or somebody turns off a fixture or faucet, you get what we call sandwiching of that temperature of that water. So you might get a little blast, a bit of a higher temperature water or lower temperature water, depending on that tap is opening or closing. When you have storage like this, that kind of dampens that impact because that temperature of that water is very consistent in the storage tank. It's only when you have that combi, when the burner actually has to ramp up or ramp down to match the load, that you end up with that kind of sandwiching impact. So there's some distinct advantages, obviously, with this particular boiler over just a regular combi unit. As well, a built-in expansion tank for the closed loop side of the system. So a lot of accessories are already kind of added onto this and installed in the correct area of the boiler for correct operation. So it leaves a lot of the kind of the guesswork out of, installing your domestic hot water systems and your boilers and your space heating with the 22F. So it's a pretty popular unit. We saw a lot of them here in Canada. I'm sure down in the US, you guys are familiar with these as well. If you're not, it's important to have a look at the heat exchanger because as you're gonna find out as we move through this presentation, the heat exchanger has an influence on whether we're going to get an EE or an EB fault, and we're going to kind of go through that and dig a bit deeper into that as we move through here. But you see just to the right of that cutaway of the 222, the heat exchanger that is inside of that particular boiler. So this is the pressure vessel, kind of a side view of it. And what you'll notice is there is a baffle plate in here. So in the middle of this heat exchanger, you've got basically your combustion side here. And of course, the flue gas side is after that little baffle plate. So what happens when this burner fires, you have combustion in this area. That flue gas is forced over that baffle and to the back area here on the flue gas here. So there's really no combustion debris that occurs in the back of section of this heat exchanger during operation. The reason why we added the baffle plate into this particular type of boiler is, if you can imagine the return pipe here at the back of the boiler, that's where the coolest water is going to move into the heat exchanger. So after it returns back from the heating system, whether it's doing domestic or space heating or snow melt, whatever it might be doing, The return water comes in the back, and of course the coldest water is back here, and this is also where the coldest flue gas temperature is going to be as well. So cold meets cold, and of course as that return water moves back to the front to become now supply water, it's getting heated as it moves through the coils of the water tube heat exchanger, and now you got the hottest flue gas temperature here meeting that hottest temperature of supply water, but giving that temperature up as that flue gas moves through those little gaps in the heat exchanger and coming out the back. So the idea is here to get the temperature of the flue gas down as low as possible by using the concept of, you know, the hottest temperature in the heat exchanger meets the hottest load side of the heat exchanger, and the coldest meets the coldest. Just kind of an idea there as far as efficiency goes, if we can add another 35 degrees of temperature drop, sensible temperature drop, as that flue gas moves through in comparison to just a wide open heat exchanger here, we will increase the flue gas efficiency when you do your combustion analysis by about 1%. So every 35 degree Fahrenheit equals about a 1% increase or decrease, depending on which direction you go, in your flue gas efficiency here. So that's the whole idea. Also, these are condensing boilers, right? What is the most important area of condensing? We need to get the flue gas to dew point temperature. I think a really good presentation that happened yesterday for some of you that missed that, talking about condensing boilers, et cetera, that Viessmann did. Jody Samuel, whatever US office, put on a presentation. So if you missed that one, it's archived, and it talks about condensing operation, et cetera. So this kind of a complement to what we're talking about here. We don't have a lot of time in this presentation to talk about dew point and how we get the boilers to condense, but this heat exchanger was built on the principle of getting that boiler to condense as much as possible. So that's where that heat exchanger, what it looks like. And of course, the flue gas now moves out the back instead of the center of the heat exchanger. It comes out the back, and then it's going to come out through the top here. So you still have the vent at the top of the boilers you see here, the concentric type of vent adapter, but the actual flue gas moves out the back side and up through the flue gas collector and then out. So that's the 222. It is a residential boiler. Even though the control base on this is essentially the same as all the other B series boilers that we're going to talk about here, it is, because of the domestic hot water built-in feature there, it really isn't meant to cascade with other boilers. You'd lose the domestic hot water function if you did that. So it's meant as a standalone kind of residential type of boiler, and it does quite a good job if you've put it into the right fit and as far as the application goes. The next boiler, there's 10 different models of this particular boiler. This is the B2HA, as well as, or it could be a B2HB. It depends on the style of the heat exchanger. So we just looked at the B2TB. That B at the end there, that's highlighted there in red, indicates that's a second generation of Vitodense 222F. There was a B2TA, and the difference between the two of those is really that heat exchanger. And that will carry on with the Vitodense 200 B2HB that we're looking at here. There were B2HA boilers in the same size or capacity as far as BTU inputs, but the heat exchanger was a little bit different in those boilers compared to the B series. And the B series basically goes from 5 models, so 5 of the 10 boilers in this 200 series are of this type of heat exchanger. So from the 68,000 BTU all the way up to the B2HB 199. We'll have that baffle plate in there. So you see a cutaway view here of that boiler as well, or heat exchanger, and you see the burner sitting up in this area, and of course the flue gas is going to be forced around and then come out to the back on this side. So the same kind of idea we just talked about as far as why we would have done that. This is the reason, is to increase the efficiency of that boiler, not just sensible efficiency, but also trying to drive that flue gas temperature down into dew point so we get the condensing aspect as well. The next series of 3, so we go from 285 up to 352,000 BTUs. We're now into the B2HA series. So this is a generation, so it's the first generation of the B2HA from 285 to 352,000 BTUs. Previously, we used to allocate our nomenclature here in kilowatts instead of in BTU. So, you know, similar boilers would have been the B2HA 80 to 100, I believe, is the number. So that would be, we've changed that in the last year and a half or so now to replicate, because most of our heat loss calculations and stuff here in North America are still utilizing BTUs. You can basically kind of get an idea of kilowatts or BTUs based on the models that you're looking at here. So that's the only reason why we're now at 199 instead of 57. 57 would have been the kilowatts of that particular boiler. All right, so the difference here in this heat exchanger is it's a center flue style. So the flue gas collector doesn't, baffle plate doesn't force the flue gas around and out the back of the boiler pressure vessel. Instead, this boiler here, this particular range of boiler, the 285 to 352, is kind of, it has two of everything. So the heat exchanger is actually two heat exchangers intertwined together and welded for a common supply outlet, but there's actually two return ports. So with two returns, you also have two flow switches, because we have to make sure there's flow on both sides of that return. So if both heat exchangers have flow through them, as well as there's two gas valves in these boilers. So they're ones that basically kind of have two, and two of the different components inside here. The reason why we would do something like this is, if you could imagine, if that was just one continuous heat exchanger and we put a pump, attached a pump to that boiler, and we turn that pump on, the pressure drop would be fairly high from the start to the finish there, as far as the amount of head pressure it would take to move a specific amount of flow of fluid through that heat exchanger. So if we cut that heat exchanger in half and weld it as we did, effectively the pressure drop is cut in half. So now we can have a pump with about half the amount of capacity, but will give us the same flow rate versus a one continuous heat exchanger. So it's all about pump head and flow rate. So these boilers, you can get up into some pretty good flow rates, somewhere around 25 gallons a minute, I think, through the boiler primary loop here. We want to make sure that head pressure is reasonable so that we don't have to oversize these pumps into some crazy areas. So it keeps that head pressure down to a reasonable level. Excuse me. That's the reason why we got with this particular type of heat exchanger. And then the final two, excuse me, are the 399 and the 530. So the B2HA series. And again, a different style of heat exchanger from the B2HB, a little different from the B2HA we just looked at, 285 to the 300. The 399 to 530, depending on your jurisdiction, you might get into a different trade qualification. Up here in the Great White North, some areas there, that would be, you'd have to have instead of a B ticket, you'd have to have an A fitter ticket. And I think in Ontario, where Mark is, it's a bit different as well. They identify the gas fitters a bit differently there.
We call it 1 and 2 here.
So 1 and 2. So which one is the A and which one is the?
One is the A and 2 is the B and I think that's different provinces do it different ways, and I'm not sure how they do it in the U.S. But generally, the break point is 400,000. At a 2 level or a B level, it's up to 400,000, and over 400,000, it's an A or a 1. Some provinces do it by appliance. Some provinces also do it by boiler plant. So if you had two 250s, that would be over 400 in some provinces, but generally it's over or under 400,000.
There you go. So it basically could be cumulative based on the boiler plant, or it could be individual. It just depends on, like as Mark said, where you're at and what the authorities have in jurisdiction determine. So that could require, because we're up over that 400,000 BTUs now with this one boiler, that you might have it might be a different person or individual that have to basically address, install, and troubleshoot these boilers. The heat exchanger, kind of getting back to that, is again multiple supply and returns. And the reason for that is exactly the same as what we just talked about previously. It's all about flow and that pressure drop through the heat exchanger. So with multiple supply and returns, we get a more even distribution of heat through the heat exchanger. We reduce that pressure drop, and we're up around about, I think it's about 38 gallons a minute of max flow rate on these boilers, with a minimum somewhere around 15 gallons a minute on these units. So some pretty good considerable flow rates through a low mass boiler, and of course to ensure that flow is achievable without a really heavy duty pump. There is multiple tappings there to keep that head pressure to a reasonable limit. So there's your the 10 boilers there. So 3 different style of heat exchangers in those 10 models to kind of consider. We move into the CU3A boiler here now, and we're in 4 different sizes of unit. With the CU3A, when you move through the different sizes, the boiler height and the boiler width stay the same. So dimensionally, the height will be the same whether you have a 94,000 BTU or 199,000. So you need the same height requirements for those. But the depth of the boiler, we just keep adding sections of plates onto that boiler to increase the amount of heat transfer area to get us into those higher BTU inputs. So the depth of the boiler is going to be different between the 94 and the 199. But a different boiler again, this is a fairly large surface area. As you can see, the cutaways, the burners up in this area. When the burner fires, the flue gas actually travels down through the vertical passageways here, much larger passageways than the Vitoden's boilers as far as that gap, a little different style, which means different type of maintenance, maybe different maintenance intervals as well, depending on where it is. The condensate also flushes down through and comes out through the bottom here through a P-trap. Large surface areas, large amount of volume of water in these boilers as well as a lot of metal content. So we actually start changing characteristics of the type of boiler we're dealing with here when we talk about the CU3A. So we're now, when we go from the 222 to the 200s here, and now we go to the Vitacross the 300, we go from low mass boilers, so, very small amount of water content, very small amount of volume or weight of metal there or mass in the boiler itself. Smaller flue gas passageways. We're trying to get a lot of BTUs into a very small area with low mass boilers. Now with high mass, we're dealing with, bigger passageways for the flue gas, as well as lower pressure drops through the heat exchanger because it's not so tightly wound and we're not getting so much, trying to squeeze so much BTUs into a very small area. So a little larger area here to deal with. The flow through these boilers as far as pressure drop is minimal, which means oftentimes you're not dealing with special piping requirements that you would have with low mass boilers. Low mass like constant flow through them. If you vary flow through low mass boilers, that's oftentimes you start dealing with cycling of the burners and inefficient operation. With high mass, because of that amount of volume of water and weight of metal, we tend to dampen the impact of varying flow rates through the boiler, so we can directly hook the boiler up to your heating system without primary loop, and we tend to have a boiler that's not going to be impacted by modulating those flow rates through the unit. So we tend to stay in operation, and the cycling issue is mitigated because of the higher mass that we're dealing with. So with a high mass boiler, and we might start, this might be a presentation in the future. We'll start talking about different piping and different reasons why we pipe a boiler this way versus that way, and high mass versus low mass is one of those things. So this kind of is a CU3A is a bit of a throwback in the fact it's actually the oldest boiler, I believe, on this presentation. It was manufactured back in the mid 90s. It took a bit of a hit as far as its operation or sales because of low mass boilers happened to explode during that particular period of time. But what we found is with these Vitacross 300 high mass boilers is they have they're less basically finicky when you have a lack of maintenance because of those bigger areas and stuff like that. They tend to be a bit more robust on that side. So kind of think about your older cast iron atmospheric boilers, they have the big flue gas passageways, etc. This is still a condensing and modulating burner. So you kind of get the best of both worlds, high mass as well as a fully condensing boiler with high delta T's across it, et cetera, to try to get you into those condensing type of operations. So it's a good replacement boiler for your your cast iron atmospherics that are out there that you need to change out. It'll also do a great job in applications where a low mass boiler could be utilized as well. So that's a CU3A. Well, that could be influenced by the EE and the EB fault. We'll talk about that. These 3 boilers that we just looked at, these 3 different types of boilers that have specific fits as far as application, all have that same control that you see on the bottom. And we'll talk about that in a minute. After we kind of look at this last boiler sitting off here on to the right, and that is a previous generation WB2B. So what we're talking about here today will actually have an influence on troubleshooting of the WB2B boiler as well. You could see an EE and an EB fault on a WB2B boiler. So another 7 sizes of boiler here from 67 up to about 370,000 BTUs. The difference really between these is the interface that you see at the bottom here. So you've got the black control on the left and the white control that you see on the WB2B boilers. What the big difference there is the number of buttons that you're seeing. So a lot of buttons on the older generation WB2B, the control platform, really not a big difference between the two generations. Other than that, that interface is significantly different. So we used to use a lot of symbols, you know, little pictures on and stuff like that to identify what that button would do, its function, and lots of good information in the manuals if you had it to kind of help you navigate through that. Whereas the motor control here has all those same features on it, only it's in a text base. So now you go to a menu screen, you scroll through, you pick what you want, and you just keep digging deeper as you move through the different menus. So a little bit of a different setup, same platform, but the interface there is significantly different. So as far as what the control looks like, you see in front of you here, if you look at the far left of the control, you'll see that little red dot. That's the fault light. So if an EB or an EE fault is occurring, that light is going to be flashing on the left-hand side. The little V, inverted V, is on both controls as well, the WB2B and the B2 series boilers. And that's in the same position. That little inverted V is actually a little communication port that you can that we can load information and access information on that particular boiler if we are standing in front of it with a special software tool. The green light there, LED, is just for power. So if you were going way back in time to the WB2A boiler, Vitodens 200, the first low mass condensing boiler that Viessmann brought to North America here way back in 2002, I think, or earlier. That green light would actually have been indicating that burner was firing. And I remember the first time we actually changed out the WB2A here in our lab and put a new WB2B boiler in there and turned it on, and I couldn't believe how quiet it was firing, because I thought that little green light on the WB2 also meant that that burner was actually in flames. So it is not an indication that the burner is firing like it did in the WB2A. That little green light just indicates that when you hit the power button, that thing is actually powered up. So green light's just powers on. To the right of that is the R button. So when the control says combustion control or lockout, you must push the reset button. It's a little square with an R on it here that we see on the newer control. On the older control, it's a little circle there with a little reset symbol on it that we would push to basically reset the burner control and get it basically back into trial for ignition at that point. Power buttons on the left or right-hand side on both controls. You see the power here, and of course the screen where the fault's going to occur will be right here. And then of course there's a lot of buttons here on the WB2B. All that stuff is now contained in the a series of half a dozen buttons here that we have on the new B2 series control. All right, so that's a good overview of what we're going to be talking about here. Let's move into the actual faults. When you walk into a boiler room and you see one of the boilers you see down below here or the WB2B, the control, when it's locked out, is going to show you a fault like that. Now, you don't know what the fault is yet until you actually push the OK button. So we push the OK button here, and now that's going to identify what that particular fault is. So if we see an EE show up on there, we have just above there, highlighted in red, the fault code display EE, and then there's a detail fault code, and we're going to talk about that detail fault code actually, I think next week. We have a presentation on coding address 38 that we're going to move through, and there'll be a little bit of information on these detail fault codes, what they mean, and what their use would be. So we'll kind of review that next week. So if you're interested, you can always sign up for next week's presentation. We know the burner's in fault mode when we see the EE. That's pretty evident because the burner's not firing. And the reason why that burner is in fault mode is the flame signal was either missing, so the burner expected to see a flame signal, and it wasn't there, or it was too weak. So there is a specific parameter. We need to get a certain threshold. The burner is looking for a specific, if when that event occurs, it's looking for a specific level of flame to be there. And if it's too weak, it's going to drop out there as well. So some instability or what have you that we're dealing with. And it gives you a list here of different things to check. And that's what we're going to do today. We're going to go through all these things fairly methodically to show you how you would check these things, not just basically kind of leave you to your own devices to try to figure out how to identify if that particular component is the problem or if it's in good condition. You don't have to worry about it. And that's kind of what troubleshooting is really. When we look at this stuff, is just a process of elimination. Modern troubleshooting is more about finding out what the problem isn't versus identifying what it is. So it's the isolate and eliminate as far as our troubleshooting. That's kind of how we're going to kind of walk through this here as we move through today. So important thing is the first step in the troubleshooting is identify what that fault is, we just did, and where it's happening. So we see here that in phase 5 is our ignition phase. And this is the point, you can see the different areas that the control is kind of monitoring as it goes through the ignition phase. And at this point, it wants to see an ionization current change. It wants to see a specific level of change there. If it doesn't meet that level, or if there's no flame that's in existence, that's when the unit's going to lock out on the EE fault. Now it's going to give it at least 3 tries before it locks out on the fault EE, which is fairly typical of most units. You can get that 3 strikes and you're out type of an idea here. That it's basically going to try, and on that third attempt, if it doesn't actually light off and see a good flame, it's going to drop out and you're going to see that EE fault appear. So the EE fault basically is just an ignition fault like we'd see on a lot of different boilers, you know, that we're control is looking for a flame and it doesn't see it, or it doesn't see one that's of a quality that's good enough to maintain that operation, and it drops out. All right, EB, a little different on the EB fault. It happens at a different phase. We look at the different boilers again, the same units here, and the B2B boiler is included in this, as well as the EE fault that we just looked at. But with EB, you have the fault there. 194 is the detailed fault code. It's in fault mode. Repeated flame loss during calibration. So it's a different fault here. So instead of no flame or weak flame signal, there was a flame the control saw. So we've gone past that phase 5. But the unit now basically lost that flame and it was doing a calibration. So we're going to have a look at what calibration here is in the next slide. But there is a process in these boilers for proper fuel-air operation here on combustion that it does a calibration cycle every so often. We'll have a look at that. And of course, it gives you the different things here to look at and the different pages based on the manuals where you'd want to basically reference. This is right out of the manual as well. So this is the phase. And now we're up around phase 6. And you can see in phase 6, automatic calibration may be initiated by the controller. So it depends on a number of things when that calibration might occur. And we're going to look at that in a second. But basically, the EB fault is a fault to deal with the burner calibrating the fuel and air ratio and not being able to complete that calibration. And of course, you get the EB fault. Important that the burner has not just the flame, but also it knows that that is a good flame as far as operation, that it doesn't have an excessive amount of gas or air, that we're dealing with some sort of an issue there. So there's a calibration phase we have to consider. And that's kind of right here. So a nice representation graphically is on the left-hand side here of what we're dealing with. So for people that are kind of, you know, into the combustion area of boilers, understand and kind of get into that area. You've got your stoichiometric combustion, right? Your theoretical combustion where you've got the perfect amount of gas and the perfect amount of air. We blend those together and we fully burn all of that air and the oxygen in the air, and all that gas is completely burnt. And that would be basically that would give you basically your theoretical levels of CO2, carbon dioxide, as well as the O2 levels that you would expect to see in your burner. But basically, Lambda is another way of looking at an air factor as far as combustion. So if you had a lambda of 1, that is that theoretical combustion area where there is 0 excess air and all of the fuel and all the oxygen basically are completely utilized and exhausted. There's no residuals left over in the flue gas. Of course, that is not again theoretical. There's always a level of excess air that is required, whether you're using an atmospheric burner, where that could be as high as 60% excess air, whether you're using a diffusion style burner, where you can get down as low as about 17% air, depending on the type of burner and manufacturer you're dealing with there. So some real high levels of combustion. And with a premix burner, we're kind of settling into that Lambda area where we're typically somewhere between about, say, 24% and maybe somewhere around about 40% excess air. And the burner control manages that. So that's what happens here automatically. So as the burner fires, gas and air are basically independent of each other. So the burner can modulate the amount of gas input as well as the fan speed to mix those different components together. The ionization is used not just for flame safety, but also to prove the quality of that particular flame. So what we're looking for there is just how well the fuel and the air are mixing together and burning. And the burner does that in an automatic fashion. So as things change, the burner's constantly making adjustments to that level. We'll have a little bit of an animation here coming up that will show you that. And one of the things you have to understand with this particular process in Lambda Pro, there's no adjustments other than the gas pressure, inlet pressure to the gas valve for the field technician to deal with here. So there is really no offset that you can dial in for the low fire, zero governor portion of the gas valve. There's no high fire adjustment level on the valve stem. There's nothing there that you can do as a technician basically to make adjustments to the gas valve physically. So there's the Lambda. This is how it looks as far as operation. So there is continuous communication between your ionization electrode and that flame signal all the way back to your control unit. And depending on the characteristics happening inside of that flame, the burner can automatically make adjustments to the amount of gas input that we're dealing with here. So with Lambda, what we're dealing with is information. So the burner is collecting data, collecting information every time it fires about the amount of fuel and air that is appropriate for the particular boiler based on the calorific value of the fuel that we're inputting in there, altitude, vent runs. There's a bunch of different variables that would be included in here, and basically adjust this to get us to optimal flame ionization. And as the burner operates here, it's just a simple flame rectification. So flame rectification means that the burner control is delivering a AC voltage to the ionization electrode. We utilize that flame here as a conduit for that electricity to basically make its way to the burner cylinder. Because the differences in the mass, the size or area of the burner cylinder versus that ionization electrode, what we tend to get is a DC signal back to the control regarding the flame safety. So what we're looking for is we deliver an AC voltage signal to the combustion area, and the burner control is looking for a microamp DC signal coming back on the burner ground. So what we're looking for here is a safe operation, but also that Lambda is always calibrating the burner to that particular point. So if we turn that burner on, and you can kind of see this little graph down here kind of mimicking that as the gas changes here, as that burner knows where that optimal area to operate is sitting and the flame signal changes, it's going to adjust the gas input, as you see here, back into those particular areas of good operation. So that's what this unit does. It's not just basically looking for that flame safety, it's also ensuring that we've got a continuous, reliable, safe operation. So things like carbon monoxide, things like that tend to be less of an issue with the Lambda Pro than with a regular type of operation, because you're continuously adjusting for different calorific values of fuel in the field with these different devices. With Lambda Pro, it kind of does that automatically for the technician. And here's another picture. This is now the same same animation basically showing you the gas changing here, and of course a flame signal making adjustment back to control, and the control itself doing a manual adjustment on the gas input to get that flame signal back into the right area. But the calibration, what's happening here is we are basically pulling the fuel air ratio continuously. So basically always making sure that we're aligning that. As the burner operates over time, of course, what's happening is things are fouling up in the combustion area. Your ionization electrodes may start to drift off of the burner mesh a bit, the distance from the mesh, etc. So as that burner continually basically does that calibration, it just adds that information to past bits of information. So as the burner's operating, and it operates for a year and a half, whatever, and through that phase, things are definitely changing with the components inside that area. But the calibration will compensate for that to make sure that the burner is always in that particular efficient level of operation. So as it adjusts that firing rate, what's going on there is when we first power that particular burner on, we hit the power switch for the first time, the burner is going to basically go to a constant speed. And at that particular point in time, usually you don't want to put your combustion analyzer in during a calibration cycle because the carbon monoxide is going to be high. It's going to be mapping that flame signal curve, ionization curve we just looked at. So it's going to go from a real fuel rich to a lean and kind of back and dial itself back in. It takes about a minute for calibration. So it gives you an idea here. You might want to hold off about a minute or so before you actually put your combustion analyzer in, because you know how expensive it is to basically send that analyzer back to get the the carbon monoxide sensor basically recalibrated or replaced because you hit it with too high a level of carbon monoxide too many times. So the calibration cycle here basically starts anytime we basically start that boiler off for the first time. So you unwrap that boiler, you mount it on the wall, you pipe it up, you vent it, you put the gas to it. As soon as you hit that switch the first time, it's going to run a calibration cycle. That first 100% calibration cycle will be attempted. And once that 100% calibration cycle is completed, it's going to do a 20% calibration cycle every so often as that burner operates, as I just talked about, to compensate for drifting of the ionization electrodes, fouling up of the combustion area, etc. So the 20% calibration is going to happen after every fault. So if we have a fault on the boiler and the unit's locked out, you reset the burner, you fix the problem, and the burner fires, it's going to do a 20% calibration right off the bat. Anytime you power the boiler off after the first initial startup, that burner, when you push that power button back on again, it's going to go to a 20% calibration after a power down and cycle back up again. And then as far as automatic calibration, we kind of saw that when we looked at the phase 6 area on the burner sequence of operation, where it talked about that automatic calibration may occur, and this is where it's going to occur. So if it's the second cycle, it's going to do another calibration, fourth cycle, 8th cycle, 16th, 32nd, 64th, 256, and 512. Now, every time you turn the burner off and back on again, it's going to start right back from the beginning again, 2, 4, 8, 16, 32nd, 64th, 256, and 512. Basically, that seems like an awful lot. 512 starts, and your burner's doing a calibration. And as that goes through those calibration cycles and adds information, what I found is that the actual level of combustion actually starts to improve. So as it adds more data, more information, your combustion efficiency actually starts to dial a little bit more in. So a little bit lower excess air numbers, a little bit higher CO2 as the burner's in operation. But we'll go through the different areas as far as what we're looking for, as far as acceptable levels of CO2, et cetera, as we move through here. To give you an idea of time reference, if you were to cycle about 5 times an hour, which is not uncommon for a low mass boiler like a Vitodens to do, depending on its, the time of the year and its operation. With about 5 cycles an hour, you're going to be somewhere around 100 hours of runtime here, and this burner is going to go through that, 512th burner start. So that's really not a long period of time when you think about the running time in a heating season. So the difference between a 20% and 100%, I kind of detailed it here a little bit, but I'll be more specific. With a 20% calibration, you're just kind of basically like it's a dampening effect. It basically averages out, adds that information into the historical data, and basically your base value is adjusted slightly based on that added on 20% calibration as the burner is in operation. If the burner goes through a 100% calibration cycle, so say for instance you replace the control or something like that on the boiler and you hit the power button and that thing goes to a brand new calibration phase, it fires up. That 100% calibration is the base value. It throws out any of the old historical information that was part of the combustion process previously. So any of that historical information is basically thrown out, and now we work off of a new base value. So it's setting it up on a new base value. And something that's important to know as well is this calibration can be conducted in the field manually. So you don't have to go to the extreme of replacing a control to go through 100% calibration. Again, you can actually physically do this in front of a boiler basically at any time. So you replace a ionization electrode or a flame rod or a gas valve or some component. It's not a bad idea to basically go through this calibration and throw out all that old information and start with a new set of base values here. So we'll actually go through how to conduct a manual calibration of these burners as we go through. Areas that we're going to be looking at today. So with the fault EE and EB, with the combustion fault, and guys that have dealt with combustion faults know in the field, it does encompass a large area. There's so many influences, both of internally, the controller, and externally, things connected to the boiler that can cause issues with the operation of that particular unit. So we're going to kind of start off with the gas delivery. Obviously, gas delivery, we are going to want to make sure that there is the appropriate amount of gas being delivered to the boiler. That's half the battle. That it's being delivered at the right amount of pressure and input. That there's no issues obstructing the delivery of that gas to the burner, and of course that we set the burner up for the proper type of gas that's actually being delivered to it. So whether it's propane or natural gas. So that's one area. Your burner tube, so the actual tube that's for combustion, that's inside the combustion area, as well as all the other components for combustion. Your gas valve, your fan, your burner assemblies, your ignition and ionization electrodes, all those things that are part of the combustion process can influence the amount, the quality of the flame that we're dealing with there, as well as if we're going to end up with an EE or an EB fault. So we're going to show you how to check all these different things out to make sure that they are functioning correctly, so that we can basically eliminate those from being the issue that we're dealing with. And just like the burner tube in the combustion area there, the fire side of your heat exchanger obviously can have a big impact on the quality of that flame. So any issues with things like instability of the flame because of back pressure problems, a fouled up heat exchanger, for instance, that's going to cause a lot of instability because of back pressure on the ignition, on the burner ignition. Condensate as well. So just like the fouling of the fire side of the heat exchanger, if the condensate's not getting away from the boiler at an appropriate speed or level there or flow, it can get backed up and start to interfere with everything from pressure inside of the combustion area. It can get into the actual combustion area itself and start, giving you evidence that there's an issue there. We'll kind of look at how to identify that condensate's actually gotten into the combustion area of your boiler. It's really evident when you see it. You might have seen it, but not really understood what it was you're looking at. We're going to identify that stuff here throughout this presentation for you, so you really have a good idea. Oftentimes, you can pick up problems with your unit when you're doing a service on it. So it's always a really good idea. And we emphasize that when we do our training here in-house, when we start pulling apart burners and doing things like that, in front of you, because of hands-on type of training, things you got to need to look for as far as, these are problems that can become larger problems. We don't actually address them at this particular point in time. So as we go through this stuff, a lot of stuff we talk about would be those external influences. Things like condensate not getting away from the boiler fast enough, or fouling of heat exchangers causing issues in the field. So we'll address that stuff here as we move forward. Combustion air and venting, these are external factors, but we are basically coming to the realization that they are a huge impact on your long-term boiler operation. How that boiler is vented, are those seals appropriate? Are we getting flue gas back into the boiler? Is it coming through the combustion air side? Are we dealing with some sort of a negative pressure issue in the building? All those things can have a real big impact and cause the fault EE and EB. So, and your venting, your exhaust and your combustion air are really long-term influences on your boiler. A brand new boiler, that fan is nice and spiffy, brand new, clean. Everything is nice and clean as far as the flow or movement of fuel and air through the burner until it gets out to ignition. But over time, things start to foul up. And of course, if there's some issues with the venting and combustion air, that's when they're really going to start to rise and kind of rear their ugly head, is when you start dealing with, a couple years down the road with, things are a little bit more fouled up, and now your pressures aren't where they were when the boiler was brand new, and you start dealing with these kind of ongoing issues. So really important to consider this venting aspect. We'll look at that, in combustion air as well, and its influence as far as these particular faults that we're dealing with today. Electrical, so controls and electrical side of it. So things, like wiring harnesses, loose connections, all those types of things. Wiring to the boiler in the field can influence as far as EE faults are concerned specifically. So we want to have a look at that. Sometimes you might have an issue with the control that could be the problem as well. But a lot of times we don't want to go to, let's just replace a control and cross our fingers as that was the problem. You're really looking at kind of the big ticket item. When you look at this little screen here that we have in front of us, you really want to have, as far as a last resort, we want to identify and exhaust any issues as far as external influences like venting and combustion air, gas delivery. Does the burner just need to be cleaned? Is there a dirty burner tube, something like that? All those things we want to identify first and kind of get down to the point where we start talking about, replacing some major components like control consoles. Very rarely are these actually the problem. A lot of times it's this stuff here that we're dealing with, but sometimes even replacing this is the influence, but back to a brand new control, new cycle, so that you might actually get some success for a short period of time, and all of a sudden the fault starts to come back again. Well, it worked for a couple months, now we're back to the same issues. That's because we never really addressed the real problem. We replaced a symptom here, and because it was brand new out of the box, it helped us for a little bit of a point in time. Very similar to things like electrodes as well. A lot of times people, with ignition faults, they'll just basically unbolt the screws here, remove the electrodes, put a new pair of electrodes in, and pack the tools back up, and away you go. There you go. It's all fixed, and we don't have the fault anymore. And then a couple of weeks later, they start dealing with the exact same fault. The only reason that they got over that little hump for a couple of weeks was because that was a new component, and basically it fouled up over a period of time, and now we're just back into the exact same particular issue. So very important to have some information on how to troubleshoot these things effectively. And these are the areas we're going to kind of go to today to properly identify these particular issues. And the last thing to look at here, obviously heat flow, more specifically EB, because we're talking about cycling of the burner. So if we don't get the heat away, this usually causes an E3 fault, a little bit different fault. But sometimes based on burner cycling, if we don't get the heat out of the boiler quick enough, and that boiler is in a combustion cycle or calibration cycle when it's firing, but it shuts off because we reached our limit, it's only going to give us, I think, 4 or 5 attempts at that before it's going to go into the EB fault, and it's going to lock out continuously until it can actually get over that particular hump. So sometimes the movement of the heat away from the boiler will cause that cycling and inability to calibrate, and you get the EB fault as a result of that. So the tools that you're going to require here, again, very important, especially if you're dealing with, and this would be, things you would need, whether or not you were going to work on this, with the manuals and, and you had this, this presentation on your device that you're standing in front of the boiler and you're kind of going through things meticulously and methodically here. These are the tools that will really help assist you in identifying and getting through those particular units. And I find that if you are missing one of these, it really makes the attempt at solving the problems of ignition faults or any faults really in a boiler that much more difficult. I'm just getting into, in my own personal life, just trying to save a bit of money here. And during the whole, lockdown thing in the last few months, I started to set up my own guitars, because that's the reason why my playing is crappy, is because my guitar is not set up properly, of course. So you try to do that with with a ruler and a couple other little pieces of equipment. It really doesn't help out. So I finally got the right tools. They came in the mail there yesterday, and how to set up the different heights and action stuff that in your control or on your guitar. And having the proper tools just go a long way for you to not only identify the issue, but identify it in a much quicker, more efficient fashion than just trying to wing it without the proper tools that you need. So let's have a little review of what we're talking about. So the first thing they mention here is a multimeter. So you're pretty much dead in the water as a technician now without some sort of a device there that you can measure things like AC voltage, microamp DC currents is always a good one to have there. Continuity, resistance, all those types of things are very valuable particularly when you're troubleshooting the faults that we're talking about here today. So a good multimeter with a lot of those features on it will help you out with good probes. Sometimes having the alligator clips in the probe will help as well, as you'll see, for checking things like ground and stuff like that. When you have just one, you need an extra set of hands, the alligator clips can come in handy. But basically get an idea there of the type of multimeter that we're looking for. And you need to have that basically to do proper troubleshooting in today's boilers, because a lot of electronic components on boilers now. So it's not so much, you don't even see a screwdriver on the screen here, other than maybe what the guy's got in his little pocket right over here. But we're talking literally about a lot of times we're using these types of devices more than our wrenches and screwdrivers in today's modern troubleshooting techniques. Other things we're looking for. So Flue Gas Analyzer is always recommended. And basically that is that's your eyes as far as combustion. You really can't set up a burner anymore. You've heard everybody talk about that. You go to trade school and stuff like that, or talk to, go to a seminar or training and guys talking about flames. And, back in the day, my father was an oil burner technician for, since the, 1970s, early 60s, I think. And, when he was going back in the day there, they could set up burners based on their eye. They'd take the little air gate. He was an oil burner tech. You'd fire the burner and you just basically take the air gate and you start moving that air gate and have a look at that flame, and nice lazy flame with some orange tips on it. You kind of set it up and away you go, right? So probably a good amount of excess air that was included in there, but they were just looking for safe operation and a good, quality flame. Yeah, today's burners, looking at that flame, sometimes if you can see it, some of our burners didn't even have a sight glass. The newer ones all have a sight glass there that you can actually see the flame, but very difficult for you to identify a flame that's in a perfect setup versus a flame that is way off. You'd have to be very extreme in what you're looking at there to actually get an idea of poor flame versus good flame just by eye. Combustion Analyzer picks up all of those pertinent bits of information, your carbon monoxide, your CO2, O2 levels. Some of them do NOx and SOx. Some of them are doing stack temperature. Some do pressures for you. So a good combustion analyzer can give you multiple bits of information as far as what that exhaust gas looks like, as far as temperature and characteristics, makeup. And a manometer or some sort of a tool or device here we see in the top left to measure gas pressure. So the first thing that's going to come out of a technician on tech support's mouth when you call them and you say, I've got an ignition fault on this burner, the first thing they're going to ask you would be, what is the gas pressure? And there are no indications of good on these meters. So they won't accept good. What they're going to want to have is an actual number as far as that gas pressure. We're going to go through that. And in order for you to measure that, you need to have some sort of a device. So whether it's a magnehelic gauge, a manometer here, these can actually be dual function. So depending on the level of accuracy, where your measurements are, a manometer, for instance, I can use a manometer not only to check and measure gas pressure, but I can also, I've got this little device right here, you see, and it's actually got a little stopper on it here. I can attach that to my manometer, and I can stick that into the vent at the top of the boiler in the Vito dens, or down at the bottom for the Vito Crossel, and I can also get an idea of what the actual vent pressure is. That's very important in combustion, right? What is that vent pressure? And I'll give you some information on that as well. But some of these things, these tools can do a bunch of different things to help you move through and get those faults done. And of course, we are all professionals here. So these tools are necessary in this profession that we have decided to be a part of. And if you're dealing with these faults, if you don't have these, you're going to be missing something. And that could be the critical piece of information that gets you from troubleshooting to diagnosing that actual problem, getting it serviced or fixed up, and moving on and having that customer end user looking at you like you are a professional, and basically relying on you and trusting you as far as your knowledge. So it goes a long way to have the right tools of the trade, basically. And these are the kind of things we're looking at. Also, finally, down here in the bottom left corner, right corner, sorry, your service manual. So whatever boiler you're working on, we need to have the manual to follow through on the different steps. This presentation is great, and it'll show you some stuff, but a lot of information in the manual pertain in there. We need to use that manual to move through these different faults. So if that manual is not on site, which oftentimes it may not be there, especially that is a WB2B that's been installed for 9-10 years now, you might have to basically find that manual. And we do have resources for you out there. So we've got the Viessmann Orange app, which you can load right onto your device, your phone, your tablet, laptop, whatever it is. And that will give you instant access to all these manuals and different bits of information that you can look at. There's a fault code checker that you can open up on this Orange app as well. So I encourage you, if you're a technician and you're dealing with Viessmann boilers, and you need to have that information, why not put this on your phone? It is a really decent roadmap as far as getting access to information when there is nobody at a phone that you can call, or you're not sitting at home, being able to navigate through our website. So you can basically click it with one button, and now bam, you've got all that information sitting there ready for you to access. You could also use our website, so Viessmann.ca, and then in this area here, we have a Pro Toolbox area. In the Canadian website, this is the .ca. And of course, we've got our current product manuals. So that would be the B2 series boilers, the 222F, B2HB, P2HA. Historic products, so the WB2B information, service manuals would be sitting in here. Fault code checker, right? You can get in there and get into fault code checking information. Technical service bulletins, those are basically information that we've discovered that will eventually make its way into the manuals, but hasn't been updated yet. There are usually bulletins sitting in here of some pretty pertinent information specific to troubleshooting. So a nice area for you to look at here. We're actually going to review this area next week when we talk about the fault code 38 in our presentation. Parts catalog, if you click on this and download that parts catalog, go have a coffee, play a round of golf, something like that. It's a pretty sizable PDF document, so it's going to take a while for you to download. But lots of good information in there for you to access on our website. If you're stateside, our neighbors to the south here, we have Viessmann US website right here. And instead of Pro Toolbox, they have Pro Resources. Similar type of information, the current products, historic product documentation, information on warranties, so some nice information there. A fault code checker sitting in there, the technical service bulletins as well. So a lot of good information that you can be at your fingertips if you have, the ability basically to have this link on your phone or whatever, if you don't want to load the app onto your phone for whatever reason. So that's all available for you at your fingertips. It's just the point of knowing where that stuff is sitting. Right?
Scott, just to add something to that,
Sure.
the parts catalog tab that's on the web page is going to be discontinued, but there is a parts application you can put on your phone called Spares. And from that, you can negotiate, or you can find all the parts you want. If you have the boiler serial number, you put the boiler serial number, and it'll give you all the parts from within that boiler, and a lot of times explosion diagrams and that kind of stuff. There is a video on our North American YouTube channel on how to use the parts app, the small parts app. So you can watch that. It is very detailed on how to work your way through that. So on the website, that parts catalog will be discontinued in favor of the online one, which is way easier for us to keep current. It's not a document we have to publish. It's going to be real-time updated.
Excellent. Okay, so and you can access that through the Orange app?
Yeah, you can actually access it through the Orange app.
Perfect. All right. So another reason to get this app on your device is basically it's going to, I think that Spares app is going to go a long ways to helping you get to that part number that you're looking for based on that boiler that you have in front of you. And it's like I've seen it actually live there, where you can click on the serial number and that exploded diagram. So it's a pretty much improved versus the hard PDF copy of the parts list that you got to kind of scroll through here. So continuing on with our fault. So now we're finally identify what that fault is, what these two faults are, where they occur, what boilers are going to be on, the tools that we need to basically help to troubleshoot here. Let's put this into practical application. So the first thing, and I like to go through my presentations kind of looking at the eliminate the easiest things first. And I always start off with ignition fault specifically, whether that boiler is an hour old or 10 years old. I always like to check the polarity of the power coming in. These are flame rectification systems, which means the power, the voltage, where it lands on the boiler control is important to whether or not we're going to have continuous operation without a particular fault. So EE fault, particularly on a reverse polarity, would be a problem. So checking polarity here, if what we need to do is basically check to make sure that the line voltage on this little green plug, which is the power plug going into our control console, I like to check it right at the source, or right at this little green plug, to make sure that the power isn't reversed somewhere else upstream of it. But this is the point where our control console is actually powered. Same spot on the WB2B, but the difference between a B2 series boiler and a WB2B series boiler is I'm powering right now, looking at the polarity on a B2 series boiler. And when I go from ground to the L on that little 40 plug, I get 119 volts, 120 volts. If I got 120 volts from ground to neutral, my polarity is reversed. So if I go from ground to neutral, I should get zero or just a smaller trickle voltage there, feedback possibly on that particular neutral. So there is a line to ground. I need to see 120 volt at this point. If I check this on a WB2B, the WB2B boiler actually works off of 230 volt. So instead of seeing 120 here, I should see around 230 volts between that line to ground on a WB2B boiler. So a bit of a difference there between the two, B series and the WB2B. And a really easy way to identify, obviously the buttons in front of them, but the WB2B series boiler also had that big power pump module that was an accessory that that was mounted on the wall. You plug that into the receptacle, and then you wired that back to the boiler. There was a big step-up transformer in that power pump module that took it from 120 volt from the wall receptacle up to 230, and that's what you plugged into the boiler for operation. We don't have that pump module style in a B series boiler. There's no amplification of that power from 120 to 230. This is a true North American boiler, so 120 volts all the ways from start to finish here on this unit. So polarity is important here, and I can give you a couple of examples. We've had a individual locally here, not on a 200 boiler, but on a smaller unit, who was getting ignition faults continuously on a boiler. And what had happened, this boiler had been in for a couple of years, they had some electrical work done on the house, and the polarity happened to be reversed at the box going to the boiler here. So now all of a sudden this boiler worked great for years, and then I started getting these nuisance lockouts. And one of the things we discussed was polarity, and of course, without the information from the homeowner that there was electrical work done there, and of course the homeowner had no clue that that would have an influence on his boiler. He never talked about it. The control console was replaced, pump modules were replaced, there was a bunch of things that were replaced, and finally the guy checked the polarity and it was reversed. So a lot of aggravation there on a simple check of polarity. I've also had ones, because reverse polarity is not going to give you 100% lockout every time. It's a very inconsistent type of situation when you reverse polarity with flame rectification. So you might have that boiler working for a week without a problem, and then it locks out like 3 days in a row. Then it operates for another 2 days, and there's a problem. So we've had, in some instances, where somebody's been dealing with that fault for a long period of time, and go there, and of course it's a polarity issue. Change the polarity, get it corrected, and that's the issue, and away you go. So it's so quick, so easy to check. I never skip this little step, regardless of the age of the boiler. And you got your meter out anyway, you might as well check it just to confirm. And again, check it always at the point on the control console here. So you can check it at your wall receptacle, you can check it at the the pump module, but you want to make sure nothing's been reversed in the wiring as we move through the control, and this would be the point. So if we have reverse polarity here, we can start working our way back to see where that polarity might have changed, or if it's right back at the source. So a nice spot to check it right there on the 40 plug on the control console. And also checking voltage AC on your ionization cable. So you check from ground, you see the ground is connected there, and I've got my meter trying to take a picture as well as hold the electrode here. So I've got a little bit of an odd holding here, but it managed it for a couple seconds to get an actual reading. So about 51.5 volts AC is what you'll see on the B series boilers, usually on that ionization cable and AC voltage. I'm not certain of what you'd see on the WB2B. I'd have to verify that and check it, but you can always check there. Basically what we're checking really is to see that there's actually a voltage there, or if there's some issue with the connection at the control console. So just measure that, and again, you got voltage, we move on from there on to the next area to kind of have a look at. And the next area to look at with flame rectification is going to be the burner ground. So as we use that ground, it's what feeds the flame signal back to our burner control. So if there's a problem with our grounding of our boiler, we're going to have a problem with that boiler actually seeing that flame appropriately and not locking out on nuisance lockouts on an EE fault, or a weak flame signal. You could get an EB fault as well, as it fires and then basically drops out. So we want to make sure that we have a good check to ground. So you could check continuity, that's fine. You can also check for resistance. That's what I've kind of done here. So you see I've got my alligator clip on the burner ground, sitting on the burner here, and I'm right back down here to the ground on my little 40 plug. So going right back to the control wiring. Put my meter across there, and we're looking for basically, a lot of times you'll see 0 here. So 0 resistance, 0.1 here. You don't want to go too high into resistance here, because we're only dealing with a microamp DC signal. So with thousands of an amp is what our flame signal coming back to the control is. So we start dealing with a high resistance on our ground here, we're going to start dealing with nuisance lockouts. We don't quite pick out that flame signal, and it drops out, and we start having those nuisance lockouts. So always a good idea to go all the ways back. So check here and right back to your ground on the control here. You can go all the ways back to your pump module if you wanted to measure that as well, just to make sure there's no issues with that signal. But very important, obviously, the control console. This is where we're picking up our amplification of our flame signal, and we want to make sure that resistance is within a good parameter. And once we get through checking a few of those things, very simple to do. That probably take you 5 or 10 minutes to get all that stuff checked out and verified, and move on to the next particular issue, and that's the gas pressure. We talked about that. Good is not a value that we can use as far as troubleshooting. We need to know specifics on what we have here for gas pressure. And this is from the manual, so you can see what we're checking here. And regardless of the generation of boiler or the type of boiler that we're talking about here today, so a CU3A, you know, a 222F, a WB2B, we're all looking for the same pressures that we want to check out here. So static pressure is one thing we want to check of the three measurements we want to deal with. We also want to make sure that gas pressure is maintained above a minimum level when we drive that burner to high fire. We don't want the burner to cycle. So if the burner gas pressure drops down too low, we actually blow the flame out with the air, and the burner's going to restart for ignition. It's going to fire up, but as it modulates, it's going to basically have that gas drop out, more air, and we're going to blow that flame out. So you get a cycling effect with a low gas pressure on high fire. And then we also want to check lockup pressure. So as the burner is in operation in a relay test on high fire, we just shut that burner off as if it dropped out on when it was in a high fire position for some reason, like it met a temperature limit or something like that. That's what it would do. We want to see if that burner locks up above that minimum. If it locks up above the minimum, the next time that burner fires, it could start getting into some instability because we're actually over firing that burner. There's more gas than what the burner control expects going in there for combustion. So you get a instability and possibly a lockout as a result of high lockup pressure. So how do we do all these little tests? Let's have a peek at it here. First thing is we're going to take that manometer or magnehelic gauge and we're going to install it, set it up so that we can actually measure at the point of reference where Viessmann would want you to have a look at that gas pressure. And that's at the inlet to the gas valve. So we're not really so concerned about downstream of the reg or any points in the manifold. We're really looking at that inlet to the gas valve. All of the gas valves have a little set screw that's highlighted here with the little yellow circle and the highlighted in red. And we back that little set screw off a turn or two. You don't have to take it all the ways out. You just basically back it off a couple of turns and turn the gas on. And we would want to see no higher than 14 inches of gas pressure here. So if we turn that, you turn that gas on, your isolation valve, open it, and that thing drops up, you know, above a particular level. So we measure pressure. So 13 and a quarter inches, that's acceptable. That's the gas pressure in my lab here that we have set up. So we got a number of boilers sitting in there. So the pressure usually sits at about, 13.25 inches on static. If I had a measurement there of, up over that 14 inches, I would have to make an adjustment to my appliance rig. So drop that pressure down below the 14 inches. We need to maintain it at that level. Otherwise, we're going to overfire the burner and we're going to have ignition faults. If it's down below the minimum of 4 inches, 1.74, we'd have to increase that gas pressure. So we need to have basically that range between about 4 and 14 inches. I like to see that gas pressure usually generally up to above that, 8, 9, 10 inches or so, just so we can compensate for some issues with maybe calibration of your devices that you're measuring those pressures with. So the other area there, we have to make those adjustments on static. Then we fire that particular burner, and we're looking for a minimum gas pressure between natural gas is 4 inches and 10 inches for propane. So if we go into a relay test here, so you actually hold the OK button and the menu key down. If you hold those two buttons down for about 4 seconds, you'll go into a service screen here. And one of those functions in the service screen is actuator test. You just use the down arrow key, highlight actuator test, push OK, and the first value is everything is off. So basically everything's going to stop. If the burner was firing, it's going to stop firing. All the pumps will stop operating. And now you, as the tech, are in complete control of all the relays in that boiler. Everything from, the domestic pump running to mixing valves opening and closing. You do all that stuff manually. You can also fire the burner. The first option is base load, which would be low fire. So that would just get the burner into that low fire operations. It would laid off and then drop down to low fire. If you go to full load and actuator test, that takes you to high fire. That's where we want to go when we're doing this little test here. That is the only way you know that that burner is in a 100% certainty that your burner is going to go to a high fire position. It's not going to ramp up to 80% and kind of hang around there. You want it to basically go into 100% output, and that's by going to relay test and going into full load. And now that you got your pressure gauge sitting there, your manometer, whatever it is, sitting there reading that gas pressure. As that burner fires up, you hear the fan speed increasing as it's ramping up to high fire. It takes 15, 20 seconds maybe for it to go into that high fire position. And we're making sure that that gas pressure stays above 4 inches or above 10 inches if it's on propane. If it drops down below, there is potential for cycling of the burner. We want to compensate for that by increasing that pressure if we can, or making some sort of a adjustment there to figure out to get that pressure up. Maybe there's something obstructing our lines or something that we'd have to investigate. That you might see that coming up here in another slide or two. But we want to make sure that at minimum, these numbers can be achieved on high fire. And I, like I say, even encourage, because calibration of our devices here may be slightly off. It might have been a year or so since we had that last into the lab to have it calibrated. Maybe having 7 or 8 inches might be a little bit better there. But yeah, at least if you've got a reading here, we can base something off of that. So these are our minimums. All right, so that's how we get into there. Once you're finished the actuator test, all you need to do is hit the back key. So that gets you out of the actuator test, and the burner, the control itself will now go right back into automatic operation. So if it was doing something like domestic hot water, or it was doing a snow melt or something like that, heating a pool this time of year, like the pool's heating up, it will go right back into that automatic operation. If it needs to fire, it'll fire. The appropriate pumps will run, all that sort of thing. So there's not really much you have to do. Basically hit the back key and you're out of the actuator test, and you're back in business. So that's the idea there, right? To maintain a gas pressure. If we drop down too low here, that's not good. We need to get that gas pressure back up in the right threshold. And finally, the third test for gas pressure, when you're specifically, I like to do these tests whether or not we're dealing with faults, because this will tell me if my boiler has potential to fault. If I fix this stuff before the fault occurs, then obviously we're not going to have a problem. As I do that high fire test, if I just turn the burner off, I'm going to basically maximize the lockup pressure that could happen on that particular gas valve. So if I hit that pressure and we just basically go back up under 14 inches, then I don't have an issue. So as long as that gas pressure stays below 14 inches when I power that control down, when the control is in a high fire on manual operation, I don't have an issue. If that pressure starts to jump up above 14 inches, I need to make accommodate that in my gas piping somehow. So I can't have lockup pressure going above 14 inches. It will become an issue. Maybe not today, but eventually you're going to get the phone call that the unit is basically locked down on something, and without knowing 100% that that control is not locking up, or the gas valve or your reg's not locking up at a high level, you can never discount that as a possible issue or reason why you're standing in front of that boiler and it's flashing a fault at you. So you want to make those accommodations, whether it's what we find sometimes is with unvented regs, you can get some spikes depending on where the location of the reg is. We're going to review that here in a little bit. The size of the reg that you're dealing with, those types of things all come into play. The diameter of the piping and how close the gas valve is to the boiler, or the gas reg is to the boiler, all have influence on what this lockup pressure is. And we'll have a peek at that here in a second. So this is the slide actually that kind of talks about that. Your gas piping. So kind of along the lines of that whole delivery thing. You'll notice this is right out of the manual. There is no appliance reg in sight here. We got a proper drip leg going into the boiler here, so there's no issues as far as any contamination of whatever crud is in the gas piping here, getting into the gas valve itself and causing a problem. Of course, that would cause an EE fault on this particular boiler if we had an issue with the diaphragm being contaminated here. You can see calcium buildup because water was getting into the gas valve and causing that particular issue. We need to make sure that we have proper gas piping, So if you're not a gas fitter and you don't know how what that gas piping should look like, you need to make sure that you got a technician that understands how gas piping needs to be done, and that they're in front of that boiler to identify any issues there. We've also found if your appliance rags are too close to the boiler, that you don't have enough downstream from the regulator once that burner shuts off and the gas valve closes to equalize that pressure downstream, and you tend to have a little higher higher gas pressure occur at this point. So a lot of these pictures you see here are the result of us being there because of faults occurring. And what we found is keeping the reg about 3 feet or so upstream of the boiler gives us enough piping there to get that pressure kind of equalized so we don't have those big spikes on lockup. Some guys will even increase the diameter of the piping between the gas reg and the boiler, so there's more area inside the piping for that gas reg to do its job properly, to make sure that we don't have a large increase or spike in our gas pressure when the burner shuts off. So just a couple of things here to kind of look at. You know, this is, if we did that lockup test and you had a high lockup pressure, you could look at this particular slide here as to some of the reasons why that might be. You're investigating everything upstream of the boiler at that point, that gas delivery, where that reg is and how it's piped, and if it's correct. Sulfidation and gas piping is occurring as well in some copper pipe. Not all copper piping has an issue. It tends to be more, I find anyway, we're looking at this, is that you know, people using the soft drawn copper that you would use for refrigeration tubing. This one here was one I was at. It was a couple years ago with an ignition fault, and there was about, I don't know, maybe 12 to 16 inches of copper pipe there, and you can see the filings here that occur. So what happens is the sulfur in the natural gas is corroding the inside of the copper line itself, and you end up with these little black flakes dissipating out of the copper, and that stuff plugs up your gas line. So basically what you'll end up with would be things like high pressure drops when the burner opens for firing. So you go from 14 inches down to 2 inches, or 14 to 0. Gas valve closes, then the pressure slowly draws back up again. A lot of that can be attributed to, if you see copper piping in your gas piping, you might want to investigate there to see if there's some sort of issue with contamination of the copper lines here with this oxidized material. So make sure you get that out. It fills up the screens of your gas valves. You can see a little bit here, not a great picture, but you see there's flakes of that stuff sitting in here. Of course, any obstructions in that gas piping that reduces the amount of flow will have a direct result in some sort of issue on ignition. So we want to address this and make sure it's not a problem when we're on site. So have a look. Sometimes just seeing that copper there is a good indication. I've had guys that have gone and, you know, I'm trying to find the pictures to add to this, but where these pipes were completely plugged full of this debris inside of there as a result. So filters, change this to stainless steel corrugated tubing, or redoing the gas piping would be a good way of basically solving this particular problem with sulfidation of the copper gas lines. And checking going back to the again, the gas valves, some of the things we talk about in the troubleshooting information that's in the manual will be things like just check the gas valve. So what are we checking for, other than the fact the gas valve is actually there? We want to check things like the power, what the voltage is. We're sending voltage to these through these wiring harnesses to the gas valve. This is also an area where the WB2B would be different from the B2HA. Remember, the information here is on a B2HA gas valve, and you can see right there it tells us what the voltage is. So we're looking for 106 volts DC on this particular gas valve. We're going to show you where to check that and how to check it out. If it was a WB2B gas valve, that would actually be about 200, and I think it's 206 volts DC, if I'm not mistaken, on a WB2B. So there'd be a bit of difference there because the voltage is different between these particular boilers. So we'll have a look at this. The 35 plug, that controls opening of the gas valve. So as the boiler basically gets a call for heat and everything goes through its trial for ignition, this is what opens up and allows the gas to move through the gas valve itself. So the burner fan is pulling that gas through. The 190 plug that you see here is what the Lambda Pro system uses as a control signal to fluctuate or modulate that gas input. So this can control the gas throughput of the valve. So it can drop it down to allow less gas if it's a high calorific value, or it can open it up more if it has a lower calorific value of gas to allow more input to get the same amount of BTU input. So these two work together, but they're operating off of different voltages. We'll have a look at that here as we move through. So the first thing that we'll look at here, we looked at the voltage on the 35 plug there already. I think we'll come back to that here in a second. But resistance on the connections on the valve on the valve coils here. The 35 plug on the smaller boilers, and this is just for the B series controls, and these numbers will change, so they're not. Don't write these in stone and say that must be this particular number. If it's off by 1/10 of a point, then we got to change the gas valve. As a gas valve is new out of the box, you measure this. It's going to be one value. You install that gas valve, fire it, doing a domestic hot water load, whatever, for 20, 25 minutes, and then check that resistance. It's going to be very different because now that gas valve is a little bit warmer, a little bit hotter as the power moves through it, and the resistance, of course, is going to climb up a bit. The idea here is more checking to see what that resistance is. If it's really far off, if it's, basically if there's an infinite amount of resistance there, it will prove that that gas valve is not in a working form, and you can replace a gas valve. That was your particular problem. So on the 190 plug, we're looking at, so that's the one basically with the white plug connected to it with only two wires connected to it. The smaller gas valves are about 75 ohms of resistance on that 190 valve plug connection on the gas valve. The larger one's about 20 ohms of resistance. So just some benchmark numbers there for you to reference. What you're looking for there really is the open circuit, as I see here in the middle, where I go across those stems, and of course I don't see any resistance there, or infinite amount of resistance is a good indication that that gas valve is not operating correctly. On the smaller gas valves, larger gas valves on the 35 plug, which is measuring right here, I have in K ohms. So 1.6 K ohm on the small gas valves, about 0.6 K ohm on the 35 plug on the larger gas valves. That would be basically the gas valves you'd have in the larger 399 and 530s. Reality is all the other gas valves are the same, from the 350,000 BTU boiler all the way down to the 68,000 BTU boiler. That's the same gas valve that you would see in there. A different orifice is used for the different BTU requirements we have in there. The other thing to understand here as well is that because that gas valve is universal from one small boiler to the one that has the two gas valves on it, as we talked about earlier, it's important that you understand that there is no orifice that usually comes with that gas valve if we're replacing it. So if you found that you had a bad gas valve here, the resistance was off, you replaced it, you took it out of the box, you installed it, and you fired it up. A good chance you're going to get an EE fault on that boiler again. And it's going to be, what? That didn't fix my problem. That's got an issue. The new gas valves are basically not, the new gas valves do not come with the orifice installed. You have to take the orifice out of the old gas valve that was on the boiler and replace it. So there might be a plug in there. There might be nothing in there. But you basically ensure that if you're replacing gas valves in these boilers, that you make sure that you get the orifice of the old gas valve and plug it in the new before you install it. Otherwise, you could basically really have a head scratcher because you're going to end up probably with another EE fault if that's what you were troubleshooting. All right, let's see here. So you've got the gas valve voltage here. We talked about that as well. So this is on the 35 plug. So when I fire that burner and it goes through a trial for ignition, I can actually test it right at the control console. I can unplug the 35 plug from the gas valve itself and measure right at the gas at the plug. I find at the terminals on the control console, the terminals are right there. It's very easy for you to check it at this point. And you're looking for the 106 volts. Remember, that's in DC, so not AC. So we're checking basically across the black connection. So there's a ground and of course two black wires that are on the 35. We're checking the two outer plugs. Just like when we're checking resistance, when we check the resistance on the 35 valve coil, we're checking the two outer stems on that 35 connection on the gas valve, just to kind of give you just so you know where to check that. And the 190 plug here, I can check right at the terminals on the 190 plug. And this is modulating based on the gas input. So as the burner is modulating up, this is going to increase the voltage DC input. You're going to go from a low fire value of approximately 3.5 volts DC up to about 5.5 volts DC. So we're just checking to make sure that that voltage is there. If you have two gas valves, so if you're into the B2HA 250,000 BTU boiler up to the 353,000 BTU boiler, you would measure at both gas valves. So they're going to get the exact same voltage DC at the exact same time. They're just parallel connections. So there's no stepping of those gas valves on those two gas valve boilers that we have. Everything is basically treated as one gas valve. Everything is just parallel. So the voltage for 35 is the exact same at the exact same time, as well as the voltage here on the gas valves would be identical throughout the output. So basically the control really only sees one gas valve, even though you have two sitting in that particular area. And I'm sure that's going to pose a question mark. The other thing to look at, obviously, so now we looked at the gas valve. So what are we checking? Remember, voltage, resistance on the gas valve, make sure the orifice is installed. If we're replacing the gas valve, those things we've covered off here. The other area, when we're talking about, obviously, Lambda Pro or combustion management or flame safety, all those things would be the electrodes that we have installed in the boiler. And this is a bit different between the WB2B and the B series boilers. In the WB2B, the ionization electrode, this guy down here, was the only electrode that would actually feed back the flame signal. With the new B series, we have that electrode doing exactly the same thing. It's feeding back the ionization current to the burner control. We also use, as a second flame signal, the ignition electrode as well. So this is connected to the step-up transformer, ignition transformer here, but it also has a connection right here that goes down and actually terminates at the exact same spot on the control console as our flame rod does here, ionization electrode signal does as well. So they go back to the same spot. And what we're attempting to do here is, as our units fire here, these electrodes will start to get a bit insulated. They get a little older. And if over time, what happens is, as the burner lights off, you get this signal that's acceptable, but it takes a while for that signal basically to, those electrodes to warm up. Your ionization signal may actually dip down into this valley. And when it dips down in the valley for too long, if it stays there, we end up with that trial for ignition, trial for, again, maybe an EE fault or some other issue on the ignition side of it. With two electrodes, what happens is they heat up at different rates because they're at different distances from the burner, from the flame. The control can now have a look at which one is giving it the strongest flame signal. And the idea is to get it past that little valley here so that we get out of those little nuisance lockout areas. So adding two electrodes that measure flame signal gives the control that much more capability of verifying that there's a flame. It's not just the fact that an electrode is drifting, but also that flame is you can measure from two different sides, and we just use the strongest signal there. So as long as we have a flame and it's within the acceptable area, within the parameters the control is looking for, we're going to step over this valley and we're going to continue on in operation. So it's important to kind of note that both those electrodes are actually used in the flame signaling process. And therefore, as far as operation function, when we're replacing electrodes, it's important that we look at both those electrodes and the service side of it. Let's have a peek. We got a burner that's going to fire up here. And when that burner fires up, that's when we can actually measure a flame signal. You can see that the electrodes here, you can actually look at them. Our spark electrode is up in this area. It's going to glow a little bit quicker. You can see it glowing there now versus the ionization electrode. It's a little bit farther away. So during ignition, most likely this is the electrode that's feeding back the strongest flame signal. That's going to be the one that the system uses. Once the ionization electrode gets past that valley and it starts to get a larger surface area than the spark electrode, it's going to start to feed back that flame signal that we're looking at. You cannot actually measure or check that. Well, you can, but you don't know if the burner is in calibration. So if the burner was in calibration and you tried to measure your microamp DC signal by putting your meter in series with your ionization electrode harness, there is an amplification that happens during calibration that might make that number kind of irrelevant, only relevant to control as far as operation. But there are some areas in coding that you can look at here as far as operation. So there's a couple steps here to look at. If I fire the boiler, and if I go into access coding level 2, if I adjust this coding address 8A from 175 to 176, if I scroll to address 42 now, which is in the burner area of the coding, it's actually going to give me in real time what that flame signal is. So the burner needs to be firing while I'm doing this. I'll actually see that. If the burner's off and not firing, you're going to see some, you know, irrelevant value here at 42, 255 or something, which is kind of just kind of a standby kind of number. Only when it's firing can you actually get a reference here on address 42 of that flame signal. So it looks something like that. So if I looked at 42 and it's 86, that would tell me that was an 8.6 microamp DC flame signal, which is pretty good. So when you're looking for something usually over about 3 microamps is the acceptable level. If the burner is locked out on a fault, if you go to address 42, you're not going to see anything that's going to help you. If I go to address 48, so if there's an issue as far as a lockout, I go to address 48 and I look at that number, and if that number is less than 9, the problem with the unit is probably the electrodes. So replacing the electrode is going to basically solve that particular fault. At least a really good indication. That's a good bet that that's the problem. So this address 48 gives you basically the quality of the flame signal. How well is that measurement? How well are those electrodes actually operating or functioning? And generally speaking, we want to see a number over 10. If you look at address 48 and it's over 10, your electrodes are most likely not the problem that we're dealing with here as far as the EE or EB fault. But if it's down below that 9, generally speaking, if it's down below 5, that boiler probably will not relight again. You're probably not going to get into an ignition that's going to be acceptable to the burner control. So that would require direct replacement of the electrodes. So just a couple of areas there for you to check, have a look at, where you don't have to use your meter. The control actually gives you that information right up front, and actually a little bit more information than just flame signal, also telling you the quality of those electrodes in operation. The electrodes themselves, as far as the taking them apart, you can also just remove them without taking the burner out. You can just pop them out here, have a look at them, and that will give you a lot of good information. You know, how fouled up are they? You can do a continuity test on them very simply. Put your meter to continuity, put it across the electrodes. You should hear a beep. These are conductive materials. They're a metal alloy. Some of it's ferritic, some of it's got some aluminum. So different types of components in here as far as an alloy in your electrodes, but they're conductors. And if I put my meter across there and I don't get any conductivity, that's telling me that electrode is getting insulated by debris. Oftentimes you'll see kind of a white powder on your electrodes. That's silicate. That's just basically debris from the combustion air coming in. And of course, it hits that electrode and it basically melts on the electrode because of the temperature of those electrodes in that area. So then when they cool down, they get that white look to them. Over time, they get brittle, so as you try to calibrate them, as we're going to have a look at here in a minute, you could actually break those. So there's a method of getting these back into kind of a good distance away from the mesh, etc. Without doing that. We'll show you here in a second. But important basically that you understand, you can actually just pull these out and have a look at them. That's not going to give you, it's going to give you a little bit of information what's happening inside of the burner area. CU3A, the same thing, we can pull those electrodes out. But it doesn't give you the whole story unless you open up the whole burner. And when you open up the whole burner, I can actually reference now the electrodes to the burner mesh. That's one of the distances that we're looking at here. So the ionization electrode for all of the burners is about 14 millimeters, and that's the same for the WB2B as well. Same distance measurement away from the burner mesh here as the B series. And then your distances and gaps. So these are all the same from the small to the big. 6 millimeters. I tried to get a reference here in inches here for a fraction. So about 1564, so it's about 6 millimeters of gap distance between the ignition electrode and the burner mesh. 14 millimeters or 35/64 from the mesh here in the ionization electrode. And of course, we need to make sure that we get the proper spark. So that's based on the reference points of the electrodes to each other here on the ignition electrode. Make sure that they're close enough here, 4 millimeters, 5/32, and then 5 millimeters distance between the electrodes here, 13/64. I use just a metric Allen key. I find it easy to slide that Allen key in there. I grab a 6 millimeter Allen key, slide it between the electrode and the mesh, and I've got a bit of wiggle room there where I can be between about 6 and 8 millimeters. So if it's going through there without too much of a problem, right, sliding it through this area here, I know that gap is in good position, and it's good to go. If it's out of spec, if it's drifting, I can heat it up with a torch, basically glow it red there, and I can bend it with some pliers, now get it back into spec, score it up, because most likely it's going to be very brittle and not as conductive as it was when it was new. And then once I score that up, I'm going to make a note. I want to come back and replace those electrodes, because more than likely that's going to fault out on December 24th at midnight, right? We've all been there. You want to be proactive, make a note, those electrodes are a little long in the tooth. It's time to make the change out in there. And they're really not that prohibitive as far as a component. And generally speaking, you can get 3 or 4 years of these electrodes if you're doing proper maintenance, et cetera, and get that good life out of those. But they are part of the ignition process. They wear over time. It's just nothing you can do about that. It's like your brakes on your car. Right? If you don't use your brakes, you're going to have some other issues. If you use your brakes, you're going to have, you're going to wear those out over time. They're going to have to be replaced. Same with your electrodes here. So, depending on cycling, depending on vent runs, a lot of things influence just how long those electrodes are going to last. But generally speaking, we get a good amount of time out of there. And when we replace them, I always recommend just replacing them both at the same time. Your Vitocrossal CU3A electrode settings, there's the gap settings for those as well. So we have a look at those. The only one that really comes out really nice as far as metric is the 3 millimeter gap between the two electrodes here. And the spark electrodes are about 1/8 of an inch. So that one there works out quite nicely on that side. But if you get a set of metric Allen keys, you can really easily check and reference these gaps to make sure we're not into any particular issues as far as that goes. And of course, the maintenance. So this is, as far as going from the simplest things to the hardest things, this really has an influence on our boilers, any boiler as far as its reliability, as far as operation. So we know what a clean boiler looks like, right? That's the one on the left-hand side here, right? Everything's nice and clean. Everything's basically opened up here. We know what a burner that's dirty or a heat exchanger that's dirty looks like. That's the one in the middle, right? They got the coffee grinds kind of layering here. This looks probably about 4 or 5 years without maintenance, kind of what the distance and amount of heat exchangers is covered up here. And you got to realize when this surface area is clean, dirty like this, the heat transfer is severely obstructed. So the flue gas really doesn't drive through this area as effectively as it does through the other areas. So we actually have to start burning more gas to get the same amount of energy out. You'll also notice we got a little tide mark here. You see how that's got a little bit of an unhappy smile there, a little bit of a frown. That is because as this burner fired, all this debris is getting into the combustion, the condensate side of the boiler, plugging up the drains, plugging up the P-trap. And now the condensate is slowly draining. And if it slows down enough, it actually starts to back up in this direction. And you'll actually see those little indications. So if you pick up this little spot right here, that tells you that this burner has been basically had that much water in it. So we're actually up to that point as far as the amount of water in this particular heat exchanger during operation. So more than likely, it probably caused a lockout of the boiler. So a good indication here, if we open up that burner and we see a lot of dampness and wetness in there, that our condensate is not getting out of the boiler quick enough. But this picture here is a bit of a puzzler. Is it clean or is it not clean? So we've got all the surface dirt out of the boiler, but the most important part of cleaning these units is getting in between these little gaps. So if we clean out these flue gas passageways, we're going to make sure that the flue gas gets out of the boiler in the appropriate amount. The condensate obviously gets out of the boiler as well. And the pressure inside the combustion area is at the right level. So we're not having a lot of instability because of a lot of high back pressure as a result of a really fouled up heat exchanger. So you can't really see if those gaps are clean or not. And that's where this little cleaning tool on the left-hand side comes in handy. It is a tool that's been developed with a serrated edge on it here, and you get a couple of replacement blades on there, which will help you get through those gaps and make sure that we clean that boiler out and get those gaps open so that we don't have that issue with combustion pressure inside of that particular unit. So clean that up, get all that loose debris out, then punch those gaps out with a cleaning tool, and then you're going to want to flush that debris out, because now you're going to have stuff that's going to be settling down at the bottom here that needs to be flushed out. And just kind of back up a bit, you can see this is actually a burner firing. So there's a flame right here, boiler's firing. We got condensate hanging on here. And notice this area here where a lot of that condensate has to form first before it gets large enough as far as a drip that's going to shear off of the heat exchanger and get down into your condensate drain. So this is where the debris from combustion and the condensate actually meet and mix. And this is, because of this is where stuff is going to stick to the heat exchanger, start to block off the flue gas passageways. And that's why it's important to use this tool to get that debris out of there. It gets sticky in there and gets kind of gunked up. You got to push through that stuff to make sure it's nice and clean and open those gaps up. So this is a really good picture to kind of get an idea of why is that debris kind of sticking down here. It's where the condensate and the combustion debris are actually going to form. Not really a big issue on the top area here. Really where that debris kind of sat right here, you can see where that stuff there's probably flue gas areas are probably plugged up there in a pretty good fashion. All right, so let's get out of that. So clean that stuff out. You can also check for vent pressure. So again, these are low fire, high fire. I had a look at a B2TB boiler that we have in our shop here, and this is going to be different based on vent runs, sidewall venting, vertical venting. 3 feet of venting versus 30 feet of venting. Hopefully, you don't have 300 feet of venting, but something along the lines there. They're all going to change these characteristics. But just as some base values again, when we're firing that boiler up, we're looking for if that vent pressure is really low, so excessively low here, that would tell me that these gaps are probably plugged up. Anyway, the fan pressure here is being exhausted because of a high pressure drop through the gaps here, that the result is a low pressure at the stack here. So we check to measure the stack right here, take that out, put our little magnehelic gauge at here, and now I can start to measure what that vent pressure is. So a really low vent pressure here by reference would indicate that I need to do some cleaning of my combustion area. It's fouled up. And that could be the burner tube as well. We'll talk about that in a minute. A real high vent pressure. So when the boiler is basically going to that pressure, and we start seeing numbers, up in the 0.8 to 0.9, that could indicate that you've got an issue in the venting side. Maybe you got an area where the venting goes horizontal for a period of time, and you got some accumulation of condensate in there, or you got something basically plugging up the venting somehow. We had an example locally here of a daycare center, and had a lot of EE faults, ignition faults in the particular boiler. Very frustrating for the owner of the building. Had a number of people go in there and do things like changing electrodes and changing gas valves and stuff like that. What it ended up being was actually proved through vent pressure, really high vent pressure. And it was just a sidewall vented boiler, a couple feet of venting on there. But what's happening was on the outside, during the recess time, little kids were putting rocks in the vent. So they were basically plugged that vent up and basically blocked it up and got a little high vent pressure in there. So that's also a good reason why you should put screens and stuff like that on the exhaust sides of your boilers, on the venting side. So especially if they're at a level where people can access them, you're not getting, golf balls and, pebbles and stuff like that being stuck or jammed in the venting there. So just an idea there, high venting versus low venting. Low vent pressure, you could be dealing with a combustion side of your boiler having an issue here. High vent pressure, you're probably dealing with something on the exhaust side here, condensate buildup, restriction in the venting there somehow, a bird's nest, wasp nest, something like that that's occurred, et cetera, that you want to investigate. So another nice reason to have that manometer that you can utilize it. On the condensate side here, the condensate needs to get out of the boiler. It's probably the #1 enemy of condensing boilers as far as operations. The condensate doesn't get out. And of course, it obstructs the passageways of the boiler and gets pressures up, and you start dealing with these nuisance lockouts. So that needs to be as direct as possible. This little gray pipe that comes out of our boilers needs to be as direct as possible to the drain. And it should not be a vapor lock connection here, not a hard connection. You see that's open there to atmosphere. That allows basically the boiler condensate to be disconnected from the actual drain side of this system. So if there's an issue on the drain side, we're not going to back that condensate up into the boiler. It's going to drip on the floor here and probably cause a phone call that we got some water on the floor there, an investigation, versus we got an EB fault or EE fault. I got no heat. I have no hot water. You got to get here right away. So that's something to look at here. Obviously, this picture down below, you see how that condensate piping is kind of all over the place. It's not direct. That'll cause airlocks, and that'll cause basically a slowing down of that condensate flow, which is going to increase the potential of us having faults as a result of condensate. You get about 6 or so feet of this condensate tube. You don't have to use all of it. You paid for it, but it's one of those things that you can cut some of it off if you don't need it all. And basically, it's going to help you log turn to make sure that if you only need 3 feet of it, just cut that pipe down to 3 feet and use that amount, and use the other stuff for something else down the road. But you basically ensure that your condensate can get out of the boiler effectively. Will go a long ways to getting that out. On the CU3A, that P-trap is basically a little bit different. It's down at the very bottom where the flue gas collector is at the bottom of these boilers. And we got a siphon here, and that drains out on the siphon side. So you can do work on that, disconnect it, and clean it out as part of the service procedure. That's what that looks like. On the WB2B and the B series boilers, the condensate piping looks a little bit different depending on the type of boiler that you're working with. So they're all a little bit different. Same concept though. We want to make sure that that condensate piping is clean, and we do service on it so that it's not a problem as we move forward. And calibration. So this is kind of the area we talked about. There is an ability of manually calibrating these particular burners so that we basically make sure that we get 100% calibration. So there's your acceptable ranges, what we're looking for. CO2 percentages and O2 percentages are in our manuals. And in order for us to do a forced calibration, obviously you want to have your combustion analyzer on hand here. We're not going to use that right away. But the first step is we go into coding level 2, and in getting into the coding level 2, we have to hold down the OK button, which my finger is covering there right now, and the menu key for about 3 seconds. And once we get into that service level, now we hold the OK button, which my finger is covering there again, and the up arrow and the back key up here, the back key, the reverse arrow key, hold that down, and that will get us into coding level 2. From there, we want to go into C code address 11. And address 11 is, if you look in our manual, is the same address you go to when you convert from natural gas to propane, or if you're going from propane to natural gas. The first step when you do a fuel conversion is to access this address 11 after you make the appropriate adjustment on the gas valve. Go to address 11, change that value to 9, and then push OK. What will happen then is your green light will flash. A little key will show up on the screen here. So you'll see that little key show up here. And once we do that, it's going to open up some addresses for us. Address 82 would be the address we would go to convert from natural gas to propane, change it from 0 to 1. If I want to force a calibration, as I have here, I go to address 85. And I go to 85, I change it from 0 to 1. And the important thing to note here, any boiler with a flow switch, so any of the B series, B2, TB, B2HB boilers, B2HA boilers that have a flow switch, the switch has to be closed, which means we have to have flow through the boiler before that burner is going to fire. So if the control isn't calling that boiler pump on, you may have to start the boiler pump as well, whether you wire it, hardwired, whatever, so it gets constant power, excuse me, or you set up a control load there so that burner has a call. As long as we get that pump to run, we change address 85 from 0 to 1, the burner's going to fire, and it's going to go through 100% calibration. So it's going to take usually takes about 2 minutes. The red and green lights are going to flash kind of alternatively. Once the red light stops flashing, the calibration is completed. I usually let it go for another 10 seconds or so. And then you have to go back to address 85, adjust it back to 0, and then go back to address 11 and basically hit OK twice. And that kicks you out of the whole combustion programming logic, so you go back into automatic operation. And now when you go back, you can have a look at that combustion. And we recommend this, generally speaking, when you're, especially when you change components, because the gas valves have a direct influence on the combustion parameters. Maybe you want to wipe out all that old historic information and start off with a fresh set of comparables here. So it's a nice feature to utilize to force that burner into 100% calibration and start off with some new set of information. All right, so that's available to us there. Finally, on the as far as talking about external influences here, we're getting a little bit long in the tooth, but the venting. So the venting we have on all these boilers, they all take concentric venting, so coaxial venting is available for all these. The Vitodens boilers are all naturally coaxial venting. They have a concentric adapter on the top, so they take concentric venting very, very easily. With a CU3A or Vitocrossal 300 boiler, it's naturally a two-pipe system. We have an adapter to take it to coaxial venting if you want to go coaxial on those particular boilers. But some general rules here. We want to make sure, obviously, any pitch back to the boiler is about, we got a pitch of about 2 inches for every meter of venting there, about a 3-degree pitch. We want to make sure the condensate will get out of the boiler. Not a lot of back-to-back 90s are recommended here. Basically, any area where you can have restrictions is we try to avoid. In the larger boilers, important to note that there was a transition adapter that should be, if it's a coaxial vented boiler, so this would be anything that's in the 4-inch venting, so that'd be the B2HA, the 285 all the ways up to the 530 boilers. If it's a coaxial vent, there should be about a 6-inch piece of transition adapter first, because the venting on the adapter is a different diameter exhaust than on the actual venting itself. If I don't use a transition adapter, there'll be an opening there. And if there's an opening there, that means flue gas can get right back in the combustion air port, and we're going to start dealing with influence of flue gas recirculation on our boilers, which really starts to create havoc as far as operation goes. Very simple to check with coaxial venting. If you use your combustion analyzer, you jam it into the port to the left of the combustion test port, and that's measuring combustion air. And basically, you put your meter, you put your analyzer on, you look at the O2, which usually sits at about 20.9 to 21%. If that starts dropping, that tells you that you've got CO2 or carbon dioxide coming back into your combustion air vent. We've got some flue gas recirculation. If it drops down below about 20.6, that's about the acceptable level. Once it drops down below 20.6, you got to investigate where that recirculation is coming from. Is it from a gasket that's displaced in the venting? Are the combustion air too close to the exhaust? Is the adapter not installed on the bigger boiler? So some investigation there to find out what that problem is. Two-pipe systems, we've got a couple of applications here. You see horizontally vented, vertically vented. We also have a hybrid system, so a vertical as well as a horizontal combustion air coming in. So the same with the CU3A. Same with the WB2B, same type of venting configurations for two-pipe. Horizontal, vertical, or a vertical exhaust and a horizontal combustion air. What we don't support would be a horizontal exhaust and a vertical combustion air. And the reason being is what you would usually notice here would be things like this on your boilers. What happens with a vertical duct? We have draft. So if this was an exhaust, it's not such a big deal. We pull some combustion air through, we cool the burner, the combustion area off as that draft occurs. But with this setup where the exhaust is on the horizontal and the combustion is on the vertical, we're actually going to start to pull that flue gas, residual flue gas back through this vent, through the boiler, back out the combustion air and out. And over time, you'll notice that you'll start to damage components because we don't want this flue gas to touch combustion air side of the boiler. So everything from our venturis get damaged. You might see some contamination, some corrosion on the side of the boilers where that flue gas comes out and it's acidic and it's damp. And of course, it starts to oxidize or corrode the enclosure of the boiler. But lots of damage can occur over a long period of time. That's what I kind of talked about earlier when we talked about venting. It's one of those things that is a long-term type of issue. It might not be a problem when you first start the burn up, but it's going to be a problem down the road. And this would be a good example of that type of situation where this is not a supported installation, but it's out there and it's a problem. So if you can identify this and you see these types of things in the actual boiler you're working with, you know the correction here is that we can't have this vertical combustion air duct as part of that system. It would have to be changed out to horizontal or room-dependent air at that point. So no to that particular type of installation. As far as single room dependent air I just talked about, you might want to make that conversion. The other situation that might occur would be if I use the air from the building, or basically the building can now influence how that air gets to the boiler. My boiler is now going to breathe the same as the building is breathing. So if there is a negative pressure in that building or positive pressure, that's how this boiler is going to breathe as well. So negative pressure means that there is more air exhausting out of the building than that's being supplied back into the building. And that can happen in a lot of today's modern construction because we build our buildings a lot tighter than they were years ago. So a lot of times we have to add ventilation air ducts to make sure we don't have that negative pressure as a problem. So what sort of things are we looking for as far as problems with flue gas recirculation and or negative pressure? Here are some pictures. A really good area to look at is on the fan itself. So if you have this particular look to your fans and you're inspecting them, this should not have flue gas touching it. This is on the combustion air side of that boiler. If you see a lot of pitting here, this is an aluminum fan. So the oxidation here occurs. It looks like a dark gray type of pitting of the fan. You see here in a larger boiler, there's a bigger CM2 commercial boiler that had a negative pressure in the building. You see how that basically started to pit around where the air comes into the fan and started to corrode away that area. So these are all signs of a problem, and eventually they will become a larger issue and start to lock out on different particular faults. Things like EB and EE faults will start to be an issue. If we just treat the symptom and replace this fan and the venturi or some of that was the problem, we're going to be back there in another couple of years doing the exact same thing. We haven't solved the issue, which is that negative pressure flue gas recirculation. So a lot of times doing your service, you can really pick this stuff up and identify it so that it basically is addressed and we don't have that particular problem. Now with the new B series Vitodens boilers, we have a little flapper that's installed in the 200s, and that was there for common venting. It's a different story for a different day, but this is our insurance that if you have a common vented system where you got multiple Vitodens boilers installed, that when this burner is firing, the boiler beside it is not getting flue gas cycling through it, because this acts as a little bit of a check as far as operation. It also helps with negative pressure. So you have a lot of negative pressure in the building. This will also help to make sure that it mitigates it to a large degree, because it closes that particular area off to block the flow of that air coming back down through the exhaust vent of the boiler. So we've made some changes here. The WB2B does not have this flapper, so that would be something that you look at. We never commented the Vitodens 200 WB2B. Only the newer B2H series boilers are compatible for common venting as a result of this little flapper being installed. So have a look. Like I say, if you're dealing with these boilers and you have these problems, probably not going to see it so much on these boilers. Flue gas recirculation, you still certainly could see if there's some issue on the exhaust side, but negative pressure tends to be mitigated on the larger B series boilers to this date. So other pictures here of flue gas recirculation for you to look at, so you're aware of them. Any staining on the outside of the heat exchanger, you see this coming around here, dried, calcified material here, staining and rusting. That's all indication. You probably have a displaced burner gasket or a vent gasket here, and as the burner's firing, got that flue gas basically escaping out of the burner enclosure, coming right back into the combustion air. That usually also will show signs at the top of the boiler where you see these little stainings. So instead of on the side of the boiler like negative pressure, if you have a flue gas recirculation as a result of a displaced gasket up here, then you'll see that staining as evidence up here. It's always important to have a look at the outside of the heat exchanger. Is there anything going on there? Any signs that there's been water kind of going around the heat exchanger? Any corrosion up here? Inside of the boiler, remember that the frown on the other refractory we looked at previously? If you have a refractory that's completely calcified here, that's usually a good indication you got a lot of flue gas moving into that combustion area. So it's being sucked in through the gas, through the venturi. And usually you're going to have evidence there. You can see evidence of staining on the gas valves. Again, the little fan here, we see that, the fan inside there having an issue where you see evidence of that flue gas getting in contact with our areas that don't want to have that combustion air being contaminated with flue gas. So all really good bits of evidence here. It's just up to us to pick them up and understand what they're telling us and actually make the physical change there to rectify that problem so that it doesn't become an ongoing issue. All right. So some of the things that we'll be looking at, vent not straight, that's going to displace the gasket inside of that particular boiler, right? And they're going to get a lot of combustion air out there. Exhaust and combustion air is too close together. Literally, as that burner fires, and this one, the combustion air is going to suck that exhaust right back in again. So these are not long-term boilers. Their life expectancy is going to be severely reduced as a result of these issues as far as the installation. And not only that, they'll be problematic as they move through their lifespan. You have icing up and debris. So this would be more in those climates that we get some pretty cool temperatures, down below, minus 30 Fahrenheit. You can get into these particular areas where we start dealing with, they just make me cold looking at them actually, where you get a buildup, what we call hoarfrost. So sometimes as that air is being pulled in, it can actually plug up the combustion air rate 100% here, as you see in this picture, and you're going to cause an EE fault at that point. Not enough combustion air for that boiler to actually fire up. So important that we have a look at those different issues and make accommodation for those as we move forward. That could mean basically abandoning the two-pipe system here because this is problematic and going with a room-dependent air, and then making sure that there's no issues with negative pressure in the building. That could be ventilation being added as well to make sure there's not a problem. So all good signs here. On the burner as well, we look at your burner here. If that burner is dirty, all this stuff here is contaminated. You can see here, your fans are contaminated, your impeller in your fans contaminated, the enclosure of the burner is contaminated. A pretty good indication that this burner tube is going to be contaminated as well, and we would need to wash that tube out. So in some presentation, we've taught you how to actually wash the burner tubes. But basically, you want to have air pressure at about 130 to 150 pounds. You can rinse these tubes out and then basically make sure they're dry, hit them with some air and dry them off to make sure that the tubes are not impacted by this combustion debris as well. But over time, the contamination of combustion air is going to be costly as far as component replacements. Things like fans, venturis, and tubes will be an issue here. So as we clean the boiler, we want to make sure that we get all this debris out so it doesn't become a legacy for that unit over a long period of time. Addressing it now ensures that in the future it's not the issue that we're standing in front of that board dealing with troubleshooting different types of faults or problems. All right. So again, as we talked about before, you looked at that fan pressure at the exhaust, at the vent adapter at the top of the boiler, and all this stuff is going to influence that. So if we start dealing with issues like that, it usually goes back to a source of a lot of contamination in the boiler. So we need to basically avoid all that contamination. So that could mean moving different things out of the boiler rooms that we have stored in there. Basically anything that ends with an IDE is probably not recommended to be stored in a boiler room. Things like chlorides and bromides and things like that, pool chemicals, your salts for your water softening, stuff like that, not a good idea. And you know that based on if you've ever went into a boiler room with a lot of those things hanging around and you look at the copper piping where it starts to get a lot of corrosion, stuff like that on it. So avoid these things in your mechanical rooms. Avoid them from being part of the contamination of combustion air as well. Things like having combustion air directly next to a pool exhaust, for instance, very bad idea. The chlorine in that exhaust air will be sucked back into the boiler combustion air, and that is a bad thing for your boiler. Any chlorine-based stuff will start to pit the stainless steel and be a problem for the boiler as far as operation. So just have a look at the information here and just make sure that the contaminated combustion air is rectified. We need to fix that before we move on. And finally, the last slide here. Thank you guys for hanging with us here today. The
last one here more related to EB faults and possibly even E3, which we weren't really supposed to talk about today. But basically, things like a drifting boiler sensor here. So if our temperature sensor is drifting, and as the boiler heats up, we start getting some really erratic temperatures here, that could cause the boiler cycling. And we can measure that with an ohm meter and have a look at it. So we take the leads off and have a look at what that sensor is. And oftentimes, if we measure it at room temperature, it's going to be accurate. We need to measure it as the boiler is hot. That gives us a really good idea of what that if that temperature sensor is drifting or not. So usually you're going to want to have a look, fire the boiler up, have a look at that, and then measure that ohms in reference to a known temperature, so that we can make sure that we don't have a problem on that. So very simple, just to measure the resistance here. And there is a graph in the manual that we can get based on that resistance here, what that actual boiler temperature, what that feedback temperature is telling the boiler it's at. So if we have drifting of our boiler sensor, it can cause cycling, which indirectly will cause calibration issues, which could cause the EB fault. Our pumps, our circulators, we give you this little little carrot here when you come into our classes. These little pump indicators or pump spinners, basically just works off of magnetic creation in the impeller of the rotor and the stator, of the pump here. So as the pump is operating, we put this little pump spinner up against the head of it, and if that magnetism is present there, it'll actually start to spin that little spinner, and it'll go in the direction that pump is actually moving. That only tells you got power on the pump. It actually doesn't tell you actually have any flow. So if that pump is basically drawing real high amps, you might see that pump spinning, but we don't have enough flow rate there. It can start to cycle the boiler as well, and you might have a problem there. A more appropriate way of measuring performance of a pump is to reference the amp draw. So you grab the line voltage lead to the circulator, put your clamp on ammeter, or if you have an ammeter that you put in series here, put it in series with the line voltage, and then you get that measurement of that amp draw and compare that to the actual performance of the pump. Where is it supposed to be versus what you actually read here? And if you start reading real high amps in comparison to what the actual number should be, it's a pretty good indication that pump is starting to go, and you may have to replace that pump, and that might fix your issues with the cycling of the burner and EB faults specifically. And finally, kind of in conjunction with the pump here would be the flow switch. So with a flow switch, basically it's just continuity. It's just a proof of closure. So it does nothing else, but it only knows one particular point, and that's the point of closing. So it has a minimum flow rate that we need to maintain. If that flow switch, because it's in the piping here, if that flow switch basically is introduced to a lot of debris that's in your fluid that's going around your heating system, it can get gummed up, and it might actually stick in the closed position or in the open position. If it sticks in the closed position, basically the burner would fire even without flow. And of course, what's going to happen there usually would be an F2 fault. You'd end up with a fixed high limit fault causing a lockout. But sometimes if that pump is still running, but you got a lot of issues with as far as amp draw, as we just talked about, you could start dealing with a lot of cycling of the burner, which would lead you into the EB fault. So it's not a bad idea with EB fault, just to verify these little points here. It doesn't take very long to kind of to look at these to make sure that they're not an issue. Matter of fact, on service, you're probably going to do a few of these things anyway. You're probably going to check the continuity of that flow switch with the control off, just to make sure that flow switch is in good working condition. As a safety, you want to make sure you check those things out anyway. So just a couple of things there to have a look at on that EB fault, on top of the stuff we just discussed in the previous slides. And that's all I got for you. I know I was a bit long-winded there today, trying to cut it short, but I think I actually did the opposite. My apologies. I hope you found the information useful. And like I say, we have recorded this particular presentation. It's going to be put up on our YouTube channel, available for you in the future to utilize. So thanks very much. I don't know if we have any questions.
All the questions we dealt with, and actually none of them actually had to do with this presentation. So we'll have to look at those and look at what we could do. Somebody was asking for more difference in the actual physical maintenance between the Vita Crossel and the Vita Den. So maybe that'll be a topic
That's a good
for our
one.
webinar.
And that is actually a good point to note there, Mark just mentioned, is if you guys have, this is a really good forum as well to kind of say, it'd be really interesting if you could cover some of this stuff. Because if we get enough quorum of people saying this would be an interesting topic, then, Mark and I will definitely pick that up and run with it. So we really want to make sure you guys get the information that you need in a timely fashion where it's available so that, it's going to be useful to you. So, like I say, this stuff here a lot of it was part of, just, tech calls, job site visits, information from engineering and our other peers, and put it in this context so you guys have this in a good, useful form. And we want to do that with a lot of other different topics as well. So if there are things out there that you're interested in that you think would be an interesting conversation for us to have with you, then by all means mention that stuff, and we'll do our best to get some sort of a presentation evolved onto that.
Yeah, and you can also send an email to us at academy.viessmann at viessmann.ca or .com rather, and
Yes.
we'll get that. So if you say, hey, I'd like to have a webinar on this, then we'll look at that. So easiest way to do that is just at academy@viessmann.com, and it'll get to us, and we'll be able to look through that.
Yeah. All right. So we're up again. If no other questions there or whatever, we're up again next week, I think. And we take a little bit of a hiatus, a little break after next week. But I think we are moving on to, which is kind of interesting, kind of leads into this, after this particular presentation. But we're going to talk about a particular fault code in these boilers, address 38, I think is the next one up on our list for a week from today. So if that's of interest to you, you might want to sign up for that one as well. I think we got another presentation going on tomorrow. We've got Jay is going to be doing a presentation. So we've basically trying to hit you with a lot of nice bits of information here, all on different topics, but all stuff that's very useful for you guys moving forward. So hope you guys are signed up for that one if you got the time to take it in. But on my behalf, and Mark, thank you guys for staying with us. And look forward to seeing you guys again.
Okay. Have a good day.
Take care.